Hi, my name is Bernardita Ried. I'm a master's student of physics at the University of Chile and also a program student at the University of Munich in Germany. Today, I'm gonna talk a little bit about the Hubble-Lemaitre law and also how we can use the method of least squares to estimate a super important quantity called the Hubble constant that helps us to understand what is more or less the size of our universe. But to understand what we're gonna talk about, or what is the Hubble-Lemaitre law, we should go back in time 100 years ago, more or less, and see this magnificent plot that was published by Edwin Hubble in 1929 in a famous paper in which he somehow derived the following relationship between the velocity of galaxies and the distance they have from Earth. So in this plot, we see that the y-axis relates the recession velocity of galaxies, while the x-axis relates the distance that these galaxies have from Earth. And what he and also George Lemaître in 1927 realized that as we look further in the universe, galaxies would have a larger recession velocity with respect to Earth. And the explanation they both gave to this unexpected result was that the universe was expanding. And we know nowadays that that's true, but for the time, it was a complete surprise and it changed the way we understand our universe. Actually, some years before, Albert Einstein published his famous paper about general relativity in which he proposed a universe that was static. So the Hubble-Lemaitre law would tell us that the velocity then of galaxies is proportional to the distance they have from Earth multiplied by a constant that is called the Hubble constant. And they both estimate this value. And the interesting thing is that even though today we have different results for this quantity, locally, this law still works. So let's talk a little bit about the cosmological context and the history of these discoveries. So the first person to talk about this expansion or to see this relationship was George Lemaître. He published his results in a not so important journal and also in French. And by doing that, people didn't learn about his discoveries. And then 2 years after, when Hubble published in English, everybody knew, and that's why this law has been called actually the Hubble law for a long period of time. But we know today that Lemaître was as important as Hubble in that discovery. But to understand what means that the universe is expanding, we should study what is a redshift. So as light is actually a wave, it has a wavelength associated. And what happens when we say that the universe is expanding and these galaxies are moving further away from us, we actually mean that the space between us it's getting larger, let's say. And when that happens, the waves of light suffer these and their wavelength expands. And therefore, the type of light we observe is different. So for example, if we are looking further away in the past in the universe, when a galaxy emitted some light, maybe when it traveled to our telescopes, it got so much expanded that if it was originally, let's say, optical light, now it's infrared. And given that red color is associated with waves that have larger wavelengths, we would say it got redshifted. So we are able to quantify this effect. And we also relate it to something called the scale factor. The scale factor is a dimensionless quantity that tells us how much the space has expanded. We can say that distances, therefore, are dependent on this scale factor because the scales in the universe change as it is evolving. And so we have two types of distances. So imagine originally we have the distance between two objects, but then given the space has increased in between these two objects, we would have that the objects did not move. So we would have somehow a fixed distance, but also if we measure how much the light has traveled between these 2 points, it would be different. So we say that we have moving distances and proper distances. Proper distances would change with time, while the moving distance stay fixed because they relate the points in space. And of course, they are related with this scale factor. And why we're talking about redshift and scale factors? Well, because I wanted to arrive to this point, which is the Hubble rate. The Hubble rate is a parameter that measures how fast the universe expands by studying how this scale factor changes over time. So that's why it is a derivative of this scale factor divided by the scale factor. So it's only a parameter that depends on 1 over the time. And if we invert that, it gives us the time. And if we set our time to be 0 in what we observe nowadays, it will measure how much the universe has expanded since the first moment it existed. And that's why we use this Hubble constant. And this Hubble constant, of course, it depends on time because the universe has some time, but we also can say that it is measured in velocities and distances, because if we see this relationship, we have kilometers, we have seconds and megaparsecs. Both kilometers and megaparsecs are measures of distances. So we can kind of find a way of solving them, and we will still have 1 over time as a quantity. But the reason why it is important to use this, because we can relate the velocity of the objects that are moving farther away from us in kilometers over seconds, and we can also compare it with the distance they have from respect to us. That's the interesting reason of why we measure this quantity in such a weird combination of parameters. So, how we can derive the Hubble-Lemaitre law? Well, we just have to play a little bit. So we had this proper distance that I mentioned before with a moving distance and the scale factor. And what we can do is to derive that to obtain velocities. And the velocity of objects moving further away from us are related with the derivative of the scale factor and the original co-moving distance. Finally, we can somehow continue playing and derive that the velocity of the objects in the nearby universe are somehow related to the distance they have with respect to us, the proper distance, and some constant multiplied. And of course, this is not any longer valid for larger distances and velocities, but in the local universe, this quantity is somehow accurate. And let's see how much it is. Let's see first the Hubble measurements. This is the data that Hubble had when he was doing his research. He had distances in this R column, he had velocities, and remember, these are recession velocities. So we have positive if they're moving further away from us, negative if they're coming to us. And the different values in here are related to the brightness and the magnitude he observed, because he did not observe directly the distances, but he inferred with the magnitude, or let's say brightness, of these objects when he studied them. So what do we have in here? First, I called 3 libraries, NumPy, Matplotlib, and Pandas. And I also made a small data set in a CSV file that's uploaded in the GitHub that only includes the 2 quantities we're more interested in this problem, which is the distance we have with respect to those galaxies and the, as I said, recession velocities. The quantities are measured in megaparsecs for the case of distances, and for the velocities are kilometers per second. And we also have the names of the galaxies Hubble observed. We'll first plot the distance and velocity, the relationship they have, and we can clearly see a correlation between the variables, right? Like if we increase the distance of the galaxies we observe, we'll see increase of the velocity they have. And the question now is how we can find this parameter, the Hubble constant, that relates these 2 quantities. Well, we can use the method of least squares. And this was independently developed by different statisticians in the last centuries. I would say Gauss was the father of this method. We would have, in our case, 24 observations because we have 24 galaxies observed by Hubble. And we want to relate these 2 quantities, distance and velocity, in a linear regression. So if we scroll down a little bit, we would see how we should proceed when we want to make this correlation. These 2 quantities, x and y, will follow a linear relationship. And we would like to know what are the coefficients that describe this relationship. So x would be the independent variable, the distance, y would be the dependent variable, the velocity, and then we will have these 2 coefficients we want to estimate because they described our model. So what we can think of is that, okay, every observation I have somehow follow this model, but it is subjected to some noise. This noise can be given by systematic error, but we would like to model these three quantities and we want to estimate them. So what we can do is to say, okay, I want to estimate actually alpha, and my estimate would be called A, beta would be B, and epsilon, which would be the noise, Gaussian noise actually, would be E. And what we would do is to send all these values to the left-hand side. And if we zoom all over the noises of our observations, apply the square value of it because we would like to have them positive, and minimize that, we will actually find out equations that describe which would be the coefficients A and B in this case, or our estimates on the coefficients alpha and beta that will decrease the error. So therefore, to minimize, we just have to derive with respect to the coefficients or the estimates of our coefficients n equal to 0. That would give us two equations. And if we solve those equations, we will obtain this relationship that the best estimate for alpha, which is A, would be equivalent to this large sum, and same thing for B. So this is the method of the least squares to obtain the estimates of the coefficients of a linear regression. Let's see if it works with what we're doing. So what actually Hubble did was a least square estimate of these two coefficients and just estimate and just find out which is the relationship between these two variables by that. So the number of observations is n, that's 24. And in here, we just define the sums that you can observe, like the multiplication of observations between x and y, and sum it over all over them. And so in here, we have the coefficients or the estimate of these coefficients, and then we just plot them. And the result is pretty nice. We found out that the Hubble constant with this data is more or less 454 kilometers per second per megaparsec. And actually, it's a value that's pretty similar to what Hubble proposed in his paper. He proposed that this value should be nearby 500 kilometers per second per megaparsec. But we know nowadays that that value is completely wrong. The value we assign to the Hubble constant is near 68. And well, it depends on what you observe. But the cool part is that with this quantity, you can somehow estimate the age of the universe. So if we measure this quantity, which would be the age of our universe, well, the funny part is that our universe would be a little bit more than 2 billion years old. And actually, nowadays, we estimate is 13.8 billion years old with the Lambda CDM model, which is the model we are testing now in cosmology, which somehow, just in a few words, it relates dark matter with dark energy, and it considers that dark matter is somehow a cold quantity. But as I said, these estimates are pretty old, but the cool part is that they were accurate in the sense that actually there is a relationship between the distance and the velocity that's linear. And of course, only when we're looking in the nearby universe. But it's still super interesting to know that we can use simple statistics to derive so important information about our universe, such as it is expanding. In here, I add also some of the bibliography I used for making this nice tutorial, and I hope it's useful for you.